I suppose you can hear me. So thank you for the introduction, Arun, and thank you for the organizers to invite me for this workshop for Bala. It's my pleasure since I did first postdoc with him, so it is my honor to join this meeting. So let's start my talk. So today I will talk on analytical modeling of the extreme mass ratio inspirals, which is slightly different from the previous two talks. So let's start. So the extreme mass ratio inspirals are one of the main targets for the laser interferometer space antenna. So this is there are a few other targets, but extreme mass ratio inspiral is one of the main targets. So LISA is the mission will done by ESA, which will launch around 2034. Now LISA is sensitivity of LISA is around 10 to minus 3 hertz, which is 5 orders of magnitude smaller than that for ground-based detectors. And that means the LISA will observe the gravitational waves whose mass is around 10 to 6 solar mass, which is also larger than that will be detected by ground-based detectors. So here is the properties. Properties that EMRI has. So EMRI, I say EMRI, extreme mass ratio inspirals, EMRIs frequently. Extreme mass ratio is such that the mass ratio between the supermassive black hole and the orbiting particle is roughly around 10 to minus 6 or 10 to 6 or so. In this case, what is different from the black hole binaries detected by ground-based detector is that the orbital this extreme mass ratio inspirals has orbital eccentricity and inclination angle from the equatorial plane of a car black hole that are not negligible, which is the one of the main difficulties in computing the gravitational waves from extreme mass ratio inspirals. Then during the few years mission for LISA, then typical total cycle of gravitational waves from EMRIs will be around 10 to 6 to 10 to 5 to 10 to 6. So that means to detect and measure the information from extreme mass ratio inspirals by the LISA data analysis, one must have theoretical waveforms whose error is less than 10 to minus 5. So to detect to observe the extreme mass ratio to obtain physical information, we need very accurate waveforms to model extreme mass ratio inspirals. And as Guillaume showed this famous picture, that extreme mass ratio binary is located around this parameter region, mass ratio and separation between binaries. So in the case of extreme mass ratio, one can use the mass ratio as a perturbation parameter, but the separation of the binary could be small, such that even in the strong field, the approximation using the mass ratio as a perturbation parameter may not break down. So that means one can both use the numerical and analytical approaches to compute gravitational waves from extreme mass ratio inspirals. Then here I will focus on analytical approaches to model extreme mass ratio inspirals, but the numerical approaches can be used to test or check the accuracy of analytical approaches in the black hole perturbation theory. So then we model the X-ray mass ratio in spirals by using the X mass ratio as an expansion parameter. So at the leading order or zeroth order in the mass ratio, compact binary will follow the geodesics in black hole spacetime. This geodesics will have three constants of motion that are energy, angular momentum, and Carter constant of the particle. But if you consider the correction due to the mass ratio, then this particle will not follow geodesics anymore in the background spacetime. This then, for example, due to the back reaction of the emission of gravitational waves, the deviation of the orbit from the geodesics can be computed from the emission of gravitational waves. So suppose in this talk, if we consider the second order correction in the mass ratio, first we expand a spacetime metric by using the mass ratio as an expansion parameter. Here I show the expansion up to the second order in the mass ratio. Then we substitute this metric into the Einstein equation. Then order by order in the mass ratio, we obtained equation of motion of the particle. So here F1, F2 is the F1 is proportional to epsilon mass ratio, and F2 is proportional to square of the mass ratio. Those F1, F2 are due to the gravitational self-force. Here I only show the equation of motion up to second order in the mass ratio, because in the LISA observation for extreme mass ratio in spirals, it's extreme mass ratio in spirals. It is known that the second order self-force is necessary for the observation. Then to detect and measure the gravitational waves from extreme mass ratio in spirals, one will correlate the waveform, theoretical waveform with the data in the LISA detector. Then in this case, we should have waveform frequency very accurately, which can be expressed by the integration in terms of df/dt. F is for example, frequency of gravitational waves. For simplicity, if we consider circular orbits, then this df/dt can be expressed in terms of the ddt and df/dt. Here is the binding energy of the particle. Then those two components can be estimated as follows. Red one is the rate of change of energy of the particle, which is associated with emission of gravitational waves. So this is why red term is called the dissipative part of the self-force. And the next blue one is as a non-zero component, even in the case of geodesic orbits, because the conserved energy can be binding energy of the particle can be expressed in using the velocity of the particle and the spin of the central black hole. In the case of circular orbits, then if you notice that the orbital frequency can be expressed in this form, then one can compute df/dt even in the case of the geodesic orbits. So one will notice that in the leading order expression of the df/dt consists of first order self-force, dissipative self-force, and the geodesic part of the df/dt. So this magenta part is dominant part, and next correction is the orange part. Orange part, and first order conservative self-force is next term which should be considered, and next the second order dissipative self-force should also be considered. First, we focus on this dominant part, first order dissipative self-force. So since the first order dissipative self-force is associated with the emission of gravitational waves, constant of motion of three constants of motion of the particle can be related to the emission energy flux of gravitational waves as follows. If in the case of the radiation reaction time scale is much larger than orbital time scale. Here, Z is the inhomogeneous solution of the Tuchel-3 equation, which is the basic equation in the black hole perturbation theory. Then this inhomogeneous solution can be constructed by using a green function of homogeneous solution constructed from homogeneous solution of the Tuchel-3 equation and source term of the source term associated with energy momentum tensor of the particle. So in the first dissipative self-force, we compute those components by using energy flux of the gravitational waves. So here is the current status of the self-force, first order dissipative self-force in the post-Newtonian approximation. The first one, I show that the circular orbit case in the Schwarz shield spacetime. In this case, the waveform and the energy flux were obtained up to 22nd post-Newtonian order by, this is me. Then 22 post-Newtonian order means that V over C to 44 correction to the leading order, to the Newtonian order, I would say. If we derive the correction up to this order, then orbital cycle, error in the orbital cycle will be less than 10 to minus 2 cycles for the few years this observation. And if we consider the more realistic case, then derived post-Newtonian order will degrade, and accuracy also will be degraded. So this is, I show the dephase or error in the orbital cycle from numerical result for the case of Schwarz shield case. So the orbital cycle will be computed from this term, which is computed by the energy flux or rate of change of energy of the particle in the case of circular orbit. And then left side and right side is the early inspiral case and later inspiral case. Then horizontal axis is time in months. Then vertical axis is the error in the orbital phase or orbital cycle. So if you increase post-Newtonian order, error of the cycle will decrease even in the 2-year observation. Then for the early inspiral case, 14 p.m. order result will achieve error of the cycle in 10 to minus 5 radian or so. Then for the case of strong field, then 22 p.m. results will give you the 10 to minus 2 radian error in the orbital phase or orbital cycle. But if you add the spin parameter of the black hole, then the situation will become worse, like this. So this is the this is showing the convergence property in the post-Newtonian approximation as a function of spin parameter q, and vertical axis the orbital velocity, which is valid in certain accuracy. So that if you increase post-Newtonian order, a region of validity will become larger. But for the case of positive spin parameter, then a region of in the case of strong field region, then even the 11 PN is not enough for a rate inspiral to investigate rate inspirals for this spin value. So that these are status for the first order dissipative self-force. Then next, I will change the subject to the conservative full self-force at the first order. 2 minutes. Yes. So the 4-point particle at the first order 4-point particle, Einstein equation will take this form. Then metric perturbation will be proportional to this this term, which diverges at here x is the field point and z is the position or location of the particle. Then if this term will diverge if the field point coincides with the location of the particle. Then that means the equation of motion or self-force, first order self-force also diverges. Then regularisation is necessary. So first, the breakthrough was brought by Detweiler and Whiting in 2003. They decomposed retarded green function into this form. R is regular, and S means singular. So this S part will responsible for the singular part of the retarded green function. So singular green function is consists of the retarded green function plus advanced green function minus some symmetric tensor. Now this GS satisfies. So important things is that GS satisfies the perturbation equation. That means that GS must have same singular behavior as retarded green function near the particle. And the GS does not affect the motion of the particle. Then GR and this symmetric tensor satisfies source-free perturbation equation. That means it is maybe easier than solving the homogeneous solution of the perturbation equation, such as Ryuichi equation or Chukovsky equation. Then we subtract retarded force from singular part from a retarded force to obtain regular solution. But even in this case, each term diverges at the particle. So we need more regularization. Then so the Barack and Ori used decomposition these terms into harmonic mode. Then one will notice that this singular part can be expressed in this expression for large L. So there are terms which is proportional to L and 1 over L. If we subtract these terms, which also retarded green function has a similar form, then if we subtract this term from the retarded function, then one will obtain a regular solution which converges. Since I don't have time, but this may be almost final slide. Then by using regular solution in the previous slide, then one could obtain first order conservative self-force as well. Then there are many works to use gravitational self-force for the conservative part to check the validity in the different method by using various invariant variables. So this is summary. So since the first, in the post-Newtonian approximation in the black hole perturbation theory, we have many results for the first order self-force. For example, flux, Isco shift, and Perrier-Sloan adverse redshift observable, which I didn't explain. Then future work may be the inspiral waveform accounting of the radiation reaction or a self-force correction by using post-Newtonian approximation. So these are also future works. Thanks. Thank you for the attention.
Yeah, thanks, we can have a quick question to Ryuichi, and then we will take 5 minutes just to go over some of the things that came up. Is there any Ryuichi?
Ryuichi, the 11th, for the Kerr case, you have it only up to 11 p.m. What prevents you from going to 20 p.m.?
Yeah, maybe, but computational resource is I am using computational resources to the other work, so I don't have a resource which can be used to compute higher order for the Kerr circular case.
That's
basically computed, but may not have a dramatic improvement. Okay. I think.
Yeah, thanks, Ryuichi.
Oh, okay, for the phasing formula, I think we are working on it now. So in Paris, we are computing the most crucial piece, which is the quadrupole moment at the 4th PN order. And we already had some, let's say, rough results last year, thanks to Tanguy Marchand, the PhD student, but he left physics for ecology, not for finance. And but now we are carrying on and try to check his results, adding subtleties that were not included. Notably, we want first to have a result using the finite part regularization I mentioned in my talk, and then building on this, we will add some dimensional regularization corrections. But to have this bulk part, let's say, is quite long, even if we have a rough result. However, we are almost there. And maybe it will take one other year to get the full result under control, just for IIJ. Or maybe I exaggerate, maybe 6 months, let's say. And then having the full IIJ in dimensional regularizations, it will be, in my opinion, rather fast to compute whatever we need to have the H22 mode at 4 p.m. So I think in maybe 3 months we can do that. I mean, it's a much shorter time scale. Then we will need to compute the current quadrupole moment at 3 p.m. And this one is a bit nasty because we need to use, at least for me, because I am not used to that technique, but we need to use Young diagrams to deal with the symmetries of the tensor in dimensional regularization, because it's a current sector moment, and it needs a disorder to be dealt with in d dimensions. So this may take a while, maybe 6 months, something like this. And finally, we will need to put all together and adding some nonlinear corrections which appear in the connection between the radiative moments and the source moments, so notably instantaneous corrections, but also some coupling between tail and memory effect, but this one is easy, I think. But this is not very long, so maybe in 3 months this can be done. So I think in maybe 1 year and a half it can be done. Or let's say 2 years if we have unexpected difficulties.
Do you want to add anything to the, so you agree with the kind of estimate for the?
You see, as already Guillaume has mentioned, ADN formalism as such is not well suited to compute gravitational wave luminosities. So we are not computing now the 4 PN gravitational wave luminosity. What was done within ADN formalism is only 1 PN correction to the leading order formula. It would be nice to extend this, but it must be done in a very clever way. It means that we need some new ideas to how to do this. This is the first remark. The second is that we are trying more now to fight with tidal corrections within ADN formalism, but at this field, we just recovered 2 PN results, and unfortunately 3 PN results seems to be very complicated to achieve. They are, at least in our formalism, computational, say, difficulty is greater than computing the 4 PN equations of motions themselves. So, thank you.
I will talk later.
Yeah, Guillaume.
As Piotr said in his talk, it is crucial to have independent calculations. And as he also mentioned, there is only one computation of the flux or luminosity at 3 PN. So I would like to encourage effective field theory people to continue, because I saw that recently some hereditary next to leading order effects were computed, but to go in this direction and go to higher order to complete the flux at 4 PN also, as high as for the equations of motion. It's very important for us.
Yeah, so I think I'll just conclude with, finally, I just wanted, since it's Bala's field, you can say the final way, then we can close the session and go for coffee.
Okay, just I recall that when we started doing the 2 PN, flux, because it could be done in almost a couple of years, we were very brave, and we thought that the 3 PN would be solved in the next 2 years. It took us 10 years. Similarly, the 4 PN took another 10 years. So it looks like, we are really need to push. And as Guillaume mentioned, unless we get into something like the effective field theory, and like the particle physicists people do, you have automatic way of computing Feynman diagrams, etc. If we can get to that particular stage, maybe, we will have progress. Otherwise, I believe that the time scale seem to be quite long, and I cannot see it changing as of now based on the techniques we use today.
Okay, thank you so much. Thank you so much to all the panelists, as well as for all of you for the questions.